Hello everyone, Jim Malis again. Let's talk about chapter 12 from the 209 book, from the Katz book, Mechanics Calculus Treatment. Chapter 12, problems 8, 23, 57, 69. We're dealing with rotation and the like, rotation, kinematics, dynamics, and things of that nature. Let's look at problem number 8 first. For problem number 8, a rotating object's angular position is given by, so a rotating object's angular position is given by this, and it's going to be in radians. It's a function of t, so it's called theta of t in this case, and it's this. D squared minus 7.65 t 2.75. That's all in radians, guys. Where t is measured in seconds. Find A and B. When is the object momentarily at rest? Well, d theta dt would have to be equal to 0. B, what is the magnitude of the angular acceleration at that time when it is at rest? Even if d theta dt equals 0, d squared theta dt squared, the second derivative of the theta function, which is the same as d omega dt, might tell us something different. So what are you talking about here? They're saying, when is this theta function, when is it momentarily at rest? It'll happen when you got that equal to 0. When, that's simple as that. B, what is the angular acceleration at that point? The angular acceleration is d omega dt. D omega dt is d squared theta dt squared. So this guy right here, omega is going to be d theta dt. We want omega to be equal to 0. When's that going to happen? Well, if you take the first derivative here of theta and then set it equal to 0, that's it, you're done. The first derivative of this quantity is, we'll do it by the sum rule, just get everything done. Minus 7.65t is the same as plus a negative 7.65t, whatever. Take the derivative here, the 2 comes out. 2 comes out in front, multiplies with the 1.54, and you just got t. So you got 3.008 t minus this guy. Derivative with respect to time is that. Derivative of this guy with respect to time is 0. And we got this right here. That's 0, and we got it, that's it. That's the end of the day. I mean, that's what you got for d theta dt. That's d theta dt. Great. Now just set it equal to 0. So what we have here is 3.08 t minus 7.65 set equal to 0. Okay, that's not, we'll take care of B later. Let's take care of this one right now. Add a positive 7.65 on each side. Divide by 3.08 on each side. At t equals 0 doesn't work. T equals 0 won't give you 0 for angular velocity, but this will. So let's see what we have. There's an awful lot they're saying here. Let's just find what t is. Solve it, you got 2.48 seconds. So that's when it's going to happen. That's your answer to A. For B, alpha is going to be d omega dt, which is the second derivative of the theta function with respect to time. This is the theta function. Take a derivative of this and get that, and then take a derivative of that. Well, when you get the derivative here, you're basically doing derivative of omega. Omega is this. That's omega. That's omega. So d omega dt is the same as this, but I just got the omega because this right here is d theta dt. So d dt of d theta dt is going to be what the alpha is. Derivative with respect to time, and that's radians per second per second. It's looking like that. That's B. So A is 2.48 seconds. For problem 8, A is 2.48 seconds, and B is a constant acceleration. So in all cases, you guys, alpha is going to be 3.08 radians per second squared. So that is number 8. So let's go to 23. A potter's wheel is rotating with an angular velocity of omega vector equals 24.2 k hat radians per second. So in magnitude, regarding magnitude, everybody, that is 24.2 radians per second. In terms of vector, magnitude and direction, how it's rolling, omega vector is 24.2 k hat radians per second. The wheel is slowing down as it is subject to a constant angular acceleration. So the wheel is slowing down as it is subject to a constant angular acceleration and eventually comes to a stop. We got A and B here, guys. Here's A for questions. A is if the wheel goes through 21.0 revolutions as it is slowed to a stop, what is that constant angular acceleration applied to the wheel that made it stop after 21.0 revolutions? So somebody put the brakes on it, but the brakes took 21.0 revolutions to finally bring the thing to a stop. What kind of acceleration was on it? Well, it was a deceleration, but what kind? Let's get a magnitude and everything else. B, how long does it take for the wheel to come to rest when all that's happening? Okay, so all right, well, let's see what we can say here, guys. Regarding 23, they put it for us pretty straightforward. Let's remember some of the kinematic equations applied to the rotational realm. Not too bad at all. They're saying omega hat is 24.2 k hat radians per second. Well, that's initially how fast it's going. Let's just talk about magnitude of angular velocity. The magnitude of angular velocity is simply the magnitude of the angular velocity vector, and that's just going to come out to 24.2 radians per second. True. Let's figure out, I guess, a couple things that are going on here vis-a-vis this stuff. They're giving us information. Now we just got to know how to use it. 1 revolution is 360 degrees. It's 2 pi radians also. That's the main thing. 2 pi radians equals 1 revolution. Let me see if I can figure this thing out. There's a lot of ways you can go. I guess the way we want to say it is, there's a lot they say here. So you could do a lot here. You could make the 24.2 radians per second, you could convert that to revolutions per second. I'd rather not. I'd rather convert the revolutions to radians. It's probably a little bit easier. I think the way they're asking the questions, they want it in radians per second per second. It's got to be an acceleration. Acceleration's a vector. Angular acceleration is going to have the k hat on there as well. So don't forget that. This kind of ain't leaving the ball game anytime soon. Tell you what, you are basically, what is theta? Theta is 21 revolutions. True. Every revolution has 2 pi radians. Twenty-one times 2 is 42 times pi. That's going to be 131.95 roughly. That's the total amount of revolution that happened, total amount of angle gone through when we do this. Well, remember those kinematics, how they look a lot? The kinematics all kind of look alike. The kinematics applied to linear relationships have a certain look, and the kinematics applied to rotational relationships in physics have a similar look to those linear relationships. The linear kinematics and rotational kinematics have, linear dynamics and rotational dynamics, the kinematics associated with them oftentimes have a very, very similar look. And we've already gone there. We've already talked about that. There's a number of ways you can do this. Let's just kind of make the long story short. D equals VF squared minus VI squared over 2A. D equals VF squared minus VI squared over 2A. Sound familiar? Yeah, you can do the same thing here. You're going to say omega F squared minus omega I squared over 2 alpha. That's what I was talking about, the similarities there. All right. I guess there's an easy way and a hard way, and I think they're both pretty easy if you're careful. Why don't you multiply by alpha on each side and divide by theta? Alpha will equal omega sub F squared minus omega sub I squared over 2 theta. Okay, good enough for me. Now what does all that mean? Well, let's put it this way. The final speed when it comes to a halt is 0. The initial speed is 24.2. Theta, forgive me, I should not have been revolutions, should have been radians. They said it was 22 revolutions to begin with. They said it was 21 revolutions to begin with. 21 revolutions, every revolution has 2 pi radians. Okay, it's going to be 131.95 radians. Forgive me, sorry about that. It went totally 21 revolutions. Well, 21 revolutions is 131.95 radians. 131.95 radians times 2 on the bottom here, that's 0 radians per second squared. This is 24.2 radians per second. And we're going to square that as well. You grind this thing out, guys, we're in pretty good shape. What we end up getting here is negative true, absolutely true. In terms of vectors, the negative means the k-hat, it's a negative k-hat. And the negative manifests that. You don't need to get too crazy when you say it. They usually put the k-hat there. I've seen sometimes the k-hat after the radians per second. Not a big deal. One or the other is going to get you there, guys. So we're doing that. That's A. The end of all that, guys, that was A. B is saying, how long does it take to stop? B is saying how long it takes to stop. Well, I might be, I don't know, if I'm not being too presumptuous here. This should go maybe a little bit faster than we think. For 23B, how long does it take to stop? I'll tell you what. Why don't you bring omega sub f to 0? You started with an omega sub I, you've got an acceleration, and you got a time. Wait a minute, this is starting to look kind of familiar. Let me subtract omega sub I on each side, and then divide by alpha. T is going to equal omega sub f minus omega sub I over alpha. Okay. So what's the name of the game here, guys? Name of the game is you want the final velocity. This is for B. You want the final velocity to be 0. We kick this thing around and we end up finding omega sub f has got to be 0. Omega sub I is what you initially had. You got this right here. Omega sub f is 0. Omega sub I is 24.2. This is negative 2.2. The rest is just pretty simple math, guys. So let's see what we got here. At the end of the day, 10.9 seconds, thereabouts. 10.9 seconds to solve this thing. All right, so that's 23. What do we say here, guys? There's a little bit of a longer one here, but that's all right. It's all right, let's go to 57 and see what we can say here. 57 is definitely a great problem. Let's see how the whole thing's going to play out. right, well, 57, you guys. 57 says, frictional torque causes a disk to decelerate from an angular speed of 4 radians per second at t equals 0 to just 1 radian per second at time t equals 5 seconds. From 0 seconds to 5 seconds, its angular speed, ladies and gentlemen, dropped from 4 radians per second to 1 radian per second. The equation describing the angular speed of the wheel during this time interval is given by d theta dt equals omega sub naught times e to the negative bt, where b and omega sub 0 are constants. A, B, C are the questions. A, what are the values of b and omega sub 0 during this time interval? B, so what are the values of b and omega sub 0 during this time interval? B, what is the magnitude of the angular acceleration of the disk at t equals 5 seconds? C, how many revolutions does the disk make during the interval from t equals 0 to t equals 5 seconds? All right, so you've got all of this in your notes, like we've said, guys. Well, let's talk. They're telling us omega sub I, and I don't even know if I should be saying, omega sub I and omega sub naught are probably the same thing, but we don't know that. So I'm going to call it omega sub I. That's probably a more realistic and honest way to go about it. And that's at t equals 0 seconds. Omega sub f equals 1 radian per second. At t equals 5 seconds. You can write that a whole, I write seconds as SEC or just S, whatever. Interchangeable, I guess, just let's make sure we know what we're doing when we are doing this thing, guys. They are telling us, they're telling us a number of things here, so let's kind of go, let's work with them. They're telling us this is kind of the grandfather of the whole thing. D theta dt is omega sub 0 e to the negative bt. Absolutely true. So if that's the case, let's play a few games here, I guess you could say. So for the following. Omega sub I equals 4 radians per second at t equals 0. Now remember now, guys, let's be reminded, d theta dt is equal to omega in this whole setup here. If that's the case, if omega sub I is 4 radians per second, d theta dt is 4 radians per second. Omega sub 0 is, I don't know what it is. E is E. B is, I don't know what it is, but it's negative B. At t equals 0, ladies and gentlemen, I do know that. So I know this. Negative B times 0 is 0. E to the 0 is 1. 1 times omega sub 0 is 4. Well, we just answered the question. Omega sub 0 is 4. Omega sub 0 equals 4 radians per second. That's part of A. That's part of finding A. Let's go the other way. Let's see what we can. Is it true? Let's see what we can see. Is omega sub f 1 radian per second at t equals 5 seconds? Okay, go back to the grandfather equation, guys. This whole thing right here is what they gave us. This is what we're working with. Omega sub f is d theta dt. It happens to be 1 in this case. Omega sub 0, we already just solved it. Omega sub 0 is 4. So omega sub f is d theta dt. It's 1. Omega sub 0 is 4. I don't know what b is, so I don't know what negative b is, but I say at time equals 5 seconds. I got that. Let us see what we got here. Let's divide by 4 on each side. E to the negative 5b. Is that the same as e to the negative 5b? Is that 1 over e to the positive 5b? Yeah. If two things are equal, their reciprocals are equal. You don't necessarily need to do the song and dance I'm doing right here, guys. There's other ways you can approach the mathematics. What you do have to do is eventually get the right answer. Let's take the natural logarithm of each side. The natural logarithm of something exponentiated t equals ln 4 over 5. Yeah, I mean, that's a little bit of a messy number, but it's true. It's a true story. Let's see here. No, I should not have said that. That was not a t, guys. Throughout this problem, I mean, the math is correct, but I did something reckless here. Let's correct it. That's 5b. That's not 5t, that's 5b. This is 5b. So at the end of all that, that's b. All the math was the same that I did. I just got reckless. This was b. It's got to stay b. I don't know where I'm getting t. That's just b. That's b. It comes to here. If two things are equal, their reciprocals are equal. You get to here. Take the natural logarithm on each side. You get down to here. And that's where they're getting the b here. B is going to be equal to 0.277 seconds inverse seconds. It's a scalar divided by 1 second or multiplied by an inverse second. So that's some of what they're talking about there, you guys. So what are they saying here? They're saying basically for A, answering A at the end of all that, right, for 57A, omega sub 0 is 4 radians per second, and B is equal to 0.277 seconds inverse. And that's it. It's arguable in some of the operations that you do, you're almost better off leaving it like that. In some of the operations that you do, leave it as ln 4 over 5. The mathematics it's sometimes a little bit easier, less stuff with the calculator. That's your own business. That's your own business at the end of the day, guys. This is true, it works, and from there you can proceed and get everything right. That's A. The other thing they had added, that was A. B, what is the magnitude of the angular acceleration of the disk at t equals 5 seconds? How many, so let's just get there first. First things first on some of these. Let me leave some things up here. Let me take other things away. So we've said a few things. some reason this has some significance. Perhaps easier in some regards, perhaps more confusing in others. I mean, I think this is a really good way to kind of look at it, but it's good to have a specific number to actually put your mind around an actual number that might be going on, a specific number that we're used to seeing. Having said all that, all right, guys, so now they're asking for the magnitude of the acceleration for B. Well, look, if omega is d theta dt, if omega is d theta dt, alpha is d omega dt, which is just the second derivative of the theta function. The second derivative of the theta function is d omega dt, which is alpha. So, sure, the theta function's already been accounted for somehow. D theta dt, so you kind of play the game this way. Maybe make our life a little easier. Omega is d theta dt. Omega is d theta dt, and that's equal to omega sub 0 e to the negative bt. Therefore, d omega dt is equal d theta dt, dt, which looks like this. Look, at the end of the day, what does that mean? Just get the derivative d omega dt, which is, if this is omega, get d omega dt, so get the derivative of this. If omega is this, and omega is equal to that, d omega dt is the time derivative of that. Correct. That equals the acceleration. So, all right, the derivative of the exponential function is itself, and by the chain rule, you put a negative b out in front of it. Negative omega 0 b e to the negative bt. This is your acceleration function. What is the acceleration at t equals? What is the acceleration? What is the angular acceleration of the disk at t equals 5 seconds? Tell you what I'm going to do. We already discovered that omega 0 was 4. We discovered that b, right? We said a lot of things about b, didn't we? But we said b was, well, okay, well, what am I even worried about here? It's negative 0.227. It's not, I don't know where I'm getting these negatives, guys. Okay, it's just, we already got the negative here, rather. I'm sorry. There's the negative, and here's 0.227. Here's 0.277. The units are fine. E is equal to, tell you what I'm going to do. This might make it, you don't have to do what I'm about to do, but you can if you want. You got B is equal to 0.22, you got B is equal to 0.277, rather. 0.277 is ln 4 over 5. What's so easy about this? There's B for you. Times t being 5. What the heck is going on here? That'll cancel. That'll cancel. Negative 4 times this. I mean, we'll cross every bridge as we got to cross it, I guess you could say. Let me just see here for one second. 0.027 it's 0.027 more than 0.25, so it's going to be negative 1. And 0.027 is going to be negative 1.08, something like that out in front. Let me just see it. Let me look at it. Here I just actually multiplied the whole thing right across, though I didn't want to necessarily do that either. But let's see what we got here. Okay, let me not multiply this out. I'm kind of doing this in my head. Maybe I should not. Let me look at it. Let me just think about it for 1 second, guys. 92, it'll be 92 less than that. It'll be 92 less than that. It'll be 1108. Yeah, this will be 1.108. Negative 1.108. For that, and I mean, we can get in the calculator and get it, guys. Push comes to shove, we're going to get there. E to the negative ln4, which is negative 1.108 times 1 over to the negative means, well, e to the ln4, if you exponentiate the natural logarithm of 4, you got 4. So you got negative 1.108 times 1/4. And that's equal that. Well, if you divide by 4 again, you get back to this guy. Negative 0.277. Now, you didn't have to do it the way I did it, guys. But it works. Works just fine. So B, what's the magnitude of the angular acceleration? Well, you know, we could say a lot of stuff here, I guess. The acceleration is negative 0.277 radians per second. This thing slows things down. The acceleration, look, it sure looks like it. I mean, I have to look a little more closely if there's some nuance here that we're missing, but sure looks like this is a deceleration. The sign kind of conveys that. It's a deceleration going on. What's the magnitude of that deceleration? And that's the big thing. And the way that gets written is, you can write it like this. Sometimes I write two like that. Sometimes just one absolute value symbol to get the answer. And they're saying it's just this. Ain't a whole lot different, guys, right? I mean, it's, so what we got here, and there it is. That's the answer they're looking for there at the end of the day. Pretty neat, pretty interesting, the way the whole thing plays out. It came out, you know, that this guy ended up more or less by himself after you ground that out, and after you multiply, you know, the whole thing came just 0.277. The math will come out. Well, the math's going to come out just fine, guys. They're asking a pretty neat question, and let us take a look at it. The question they're asking here is, how many revolutions does the disk make during the interval? Well, they got the whole thing in radians. Thanks, right? Well, we know that every 2 pi radians is a revolution. So when we get this answer at the end of everything that we do regarding this problem, when we get the answer, we'll have it in radians, and we'll just divide by, every time we got 2 pi radians, we got 1 revolution. We'll divide by 2 pi radians at the very end, and then we'll get revolutions. That won't be a problem. So they're basically asking you, as we said, how many revolutions does the disk make during the interval from t equals 0 to t equals 5 seconds? It sure does make sense that it's a deceleration, guys. Reason for that is, remember guys, that at the way they had it set up here, at t equals 5 seconds, this thing had slowed down to 1 radian per second. At 5 seconds passed, the thing's only going at 1 radian per second. At 0 seconds, it was going at 4 radians per second. So right when it began, right when we put the clock on this thing, right when we put the brakes on this thing, right when we did whatever we did to this thing to make this function be what it is, at t equals 0 seconds, this thing was going 4 radians per second. At t equals 5 seconds, this thing was only going 1 radian per second. So at t equals 0 seconds, 5 radians per second. After 4 seconds, after 5 seconds passed, it's gone down to 1 radian per second. So from 4 radians per second to 1 radian per second in the time span of 5 seconds passing. From 4 radians per second to 1 radian per second. That's a deceleration. And that's where we were getting this. That's where we're getting this. We wanted the absolute value. We wanted the magnitude, and we got that. Okay. Looking at this, how's C going to play out? It's a classic integral problem at that point, guys. What we can say is, looking at it, let me just see here. There's enough we've said, and we've got all this stuff up here. Let's talk a bit. We know what the constants are. We know this thing had a deceleration going on, or at least it did at some point. Now, look, I'm kind of trying to play devil's advocate on this whole thing, you guys. For all we know, we could develop a function where this thing accelerates and then decelerates greatly, and at the end of it, it went from 1 radian per second to 5 seconds later going only 4, we know that, let's say at the very beginning, it was going 4 radians per second, and let's say we made it accelerate and go much faster, and then bam, make it plummet and go down to 1 radian per second, and this all happened in 5 seconds. At t equals 0, it was going 4 radians per second. At t equals 5 seconds, whatever happened between t equals 0 and t equals 0 seconds and t equals 5 seconds, whatever happened in those 5 seconds, it was initially going 4 radians per second at t equals 0, and after 5 seconds, at t equals 5 seconds, it's going 1 radian per second. So it fell from 4 radians per second to 1 radian per second. Yeah, but we don't know how that happened. It could have accelerated very, very fast and then really, really went down, so which got it to where it's going to happen. That didn't happen here. The function itself doesn't speak to us in that manner. We'll see what they say about that. Let's see what we can say, guys. So for 57C, again, we're remembering omega sub 0 e to the negative bt. We know a good amount, but we'll do what we got to do. I mean, vis-a-vis to get all this stuff done. We do know that B, we said B was 0.277 inverse seconds, which is the same as ln4, and maybe that's kind of useful. ln4 over 5, is that what I had there? Let me just make sure. Right. And that's going to be seconds inverse. I don't know. I already kind of told you. They don't matter. It doesn't, it's a horse apiece, guys. That's the same as this. So I got some stuff to it. Omega sub 0 is initially what was going on. We just said it started at 4 radians per second in speed. After 5 seconds, it fell down to 1 radian per second in speed. If it fell like that, it's a deceleration. We figured out that negative 0.277 radians per second is faithful to that being a deceleration. True. We wanted the magnitude, so we took the negative 0.277 radians per second. We just made it positive 0.277 radians per second per second. So we got that as this. What are they doing here? Well, I guess I'll tell you what. Is it true if you integrate from some theta sub I to some theta sub f, if you integrate that thing with respect to time, you're going to get, theta evaluated between these two limits. True. Yeah, absolutely true. Well, yeah, that's good. Well, I'll tell you what. Yeah, I mean, it's actually a better, yes and no. Spoke too soon here. This is true, but it's true and it's not. I mean, since you're integrating with respect to t, it's going to be a t sub I, and there's going to be a t sub f. And there's going to be a t sub f. And that's it. It's as simple as that. So what's going on here, guys? Well, d theta dt, they already told us what it was. It's omega sub 0, e to the negative bt, integrate it from t sub I equals 0 to t sub f equals 5. T sub f is 5 seconds, t sub I is 0 seconds. Integrate this thing, and you're set. A lot of looks to it. And that will get you the change, and that'll get you the delta theta. The change in theta. It'll be in radians, and then we're going to convert the radians to revolutions. So let me see what we can do here, guys. Go ahead. Do that whole integral. Let's get this whole integral. Let's figure out where we are. We'll plug in what we got to do. Well, what it's going to be is theta, delta theta, or theta. If I wrote it as theta, delta theta and theta can kind of be used interchangeably. But let's see, it's really delta theta is more realistic, but that's all an issue of semantics, guys. Do the integral here. The integral here is going to be the antiderivative of omega 0 e to the negative bt, which is going to be omega 0 over negative b e to the negative bt, evaluated between t equals 0 and t equals 5. So what's going on here? Well, it's going to be essentially this over this is going to be negative 4 over 0.277 e to the negative 0.277 t from t equals 5 to t equals 0. This is interesting. What's going to happen here, guys, is you're going to get a small number, but it's going to be negative. This is never negative. Even when there's a negative right here, it's never negative. It's just going to be a small number here. Small number times a negative is a small magnitude negative number. Put a 0 here. This is going to be a bigger magnitude negative number. A negative number minus a more negative number is a positive answer. You plug in all the stuff in there, guys. You plug in all the stuff in there and how it's all going to work out. But you plug the 5 in here, grind it out, get an answer. You plug the 0 in here, grind it out, get an answer, do the subtraction, and I got this in the notes for you as well. This is 10.83 radians. Okay, this thing was moving. This thing did move. It makes sense that it was moving. It makes sense that it did do something. It didn't just stand still. Why is that? Well, okay. I mean, it doesn't, I guess. I shouldn't. Basically, if this thing's pretty well behaved somewhat, as far as the exponential function is concerned, it started going, it was really fast, and it ended up really slow, but it never really reversed speed. So wherever it went to it, pretty much. There was never a negative velocity. I know I said hypothetically earlier, you could have something negative going on, a negative velocity. Yeah, I know. That never happens with the exponential function, though. It's kind of interesting in its own right. That thing right there is never going to be a negative number. So whatever it does, it's going to do it, but it tends to go in one direction when it's doing it, given the things that have happened here. Again, never say never, never say always on a lot of this stuff, guys, but this sounds about right. So theta is this. Theta is 10.83 radians. Is it true that every revolution is associated with 2 pi radians? The product 2 pi, 6 point something, goes into here how many times? 1.72 revolutions, and I think they wanted revolutions on this one. 1.72 revolutions. Let's make sure. I think that's what the way they asked it here, guys. Let me ask. How many revolutions does the disk make during that interval? So there's a lot here. I'm making some assumptions. Sometimes the assumptions aren't always going to work out. But this one, like I said, it started pretty fast. It ended slow. The function itself is never negative. Therefore, even though this is negative up here, I get it, e to the negative bt will never be negative. The velocity is always oriented, unchanging in its orientation. In other words, if it was positive initially that we're talking about, it's positive throughout. The smallest it can get is, technically it can't even become 0 because of if this is a non-zero number, this won't even become 0. After a very, very long period of time, it'll come close to 0. It'll take almost to infinity for it to be practically 0, but it won't ever go underneath 0. In the limit, it'll go to 0. But if the theta dt is always a positive number, positive angle is happening, is being subtended. The angle that you are accomplishing, that has happened, is going to be a positive amount of angle. Okay, and we saw that. The answer we got here was way over here was 10.83 radians, and that 10.83 radians is they converted the revolutions like they wanted is 1.72 revolutions. All right, that's 57, you guys. Let's go to problem number 69 and see how this plays out. So problem number 69, the propeller of an aircraft accelerates from rest. That means from a dead stop, not moving. The propeller of an aircraft accelerates from rest with an angular acceleration, alpha equals 4t plus 6, where alpha is in radians per second, radians per second squared, and t is in seconds. What is the angle in radians through which the propeller rotates from t equals 1 second to t equals 6 seconds? Okay, so let's see that. All right, guys. Well, I mean, we heard what it said. I think we're in pretty good shape. Let me just carefully talk about it. They want it. Now, they didn't say revolutions here. We can get revolutions pretty easy. From radians to revolutions, just divide the radians by 2 pi radians and you get revolutions. From revolutions to radians, you just multiply the revolutions by 2 pi radians and you get radians. So what is the angle in radians through which the propeller rotates? From t equals 1 second to t equals 6 seconds, given everything that's there. All right. The trick on this stuff, guys, that is d omega dt, which is d squared theta dt squared, where omega is d theta dt. That's just something we keep kind of in the back of our mind doing a lot of this stuff. There's a lot can be done here. Omega will equal the appropriate integral from an omega sub I to an omega sub f of d omega dt, that function dt will give you the change in omega. Delta omega would probably be a better way to write it, but this isn't bad either. What does that mean? Well, we're getting a change in omega, so we got to be careful. We got to be really careful here. Do the integral. They're telling us, I mean, on the back end of all this, you guys, they're telling us that alpha, which is the d omega dt that we're talking about, right? The d omega dt, they told us the alpha was 4t plus 6. So we're playing the game along those lines. This is what they told us. This is what we're going to do. So we're looking at something like that. Do the integral. And like I said, there's a number of ways to write this. Let me write it like this. Omega, again, you're assuming, forgive me, I made another mistake here. It's not omega sub I to omega sub f. You're going to get, this omega right here is really a delta omega, which is omega sub f minus omega sub I. The integral is from t sub I to t sub f. T sub I to t sub f. T sub I to t sub f. Because you're integrating with respect to time. So be careful with that. 4t. Integrate 4t, you get 2t squared. Integrate 6, you got 6t plus c. Yeah, that's true. So a number of ways you can do this. Change in speed, let me think about it, guys. It started from rest, right? If it started from rest, omega sub 0, that's omega sub I. Omega sub I is omega sub 0. Omega sub 0 is 0, and that's going to be equal to this. Okay. If that's the case, let's solve for t. Well, yeah, let's do a lot of stuff here, I guess you could say. At t, well, let's talk at t equals 0. This is at t equals 0. T naught is equal to 0. Omega sub 0 is equal to 0. And that's it. That's this. So what you got here is this. 2t squared, 6t plus c equals 0. That's all 0. 0 equals c. The constant, lucked out, the constant here at t, if t is 0 and t is 0, c's got to be 0 if that whole thing's got to be 0. So c is 0. So omega sub 0 is equal to 0, as we said. The omega function, you guys, as general, we just got ourselves out of the woods a little bit. This is the general statement of the omega function, which, by the way, is the same as d theta dt. So if we That's about it. I think that got us through maybe the toughest part of this whole thing, you guys. See how much of an angle we're going to get here. You're going to get a theta, or how about a delta theta, from the integral from t sub I, or t sub naught, to t sub f. I usually write t sub I, but they're using naught. I got to use naught then, I think. Of d theta dt, dt, which is what? That's the integral from t equals 0 seconds to t equals 6 seconds. D theta dt is the omega function. T equals 0 to t equals 6, omega is 2t squared plus 6t dt. So, yeah, this is pretty important stuff. That one right there is pretty big. This is what's going to do it. This is what's going to take the whole thing to completion. Right here, this guy. So, what we're doing, well, let's just go for it. I mean, at that point, let's just do the integral. That delta theta is the total amount of angle that gets done, which is really, well, someone just call it theta sometimes as well. Let's do the integral and go for it. Do the integral. You will integrate. The integration of a sum is the sum of the individual integrals. Tell you what, just integrate these separately, but have them together anyway. The integral of a sum is the sum of the integrals. What do we got here, guys? How about 2/3 t cubed? How about 3t squared? What do you say you take that between t equals 0 and t equals 6? Well, t equals 0. T equals 0. 0 right here, 0 right there. That's 0. That's easy. Put a 6 in here. 6 squared is 36. Times 3, that's 108. 6 times 6 times 6, I tell you what, let me cancel one of the 6's, and I got 2 times 6 times 6, which is 72, times 2 is 144. 144 plus 72 is 216. All right, 204, wait, what do we, yeah, I think, let's just, no, I'm wrong. Do it again. 6 squared is 36 times 3 is 108. 108, okay, I'm sorry about that. I made it 72. 6 squared is 36 times 3, that's 108. Here it's 6 times 6 times 6. You know, there's a lot there, if you're going to say it like that. You know, let me just multiply that in my head, guys, and kind of give you an idea where it's going to go. It's going to be 216. 216 divided by 3 should take us to 72. You double 72, you got 144. Okay, 144 plus 108 is 252. So for some reason, were they saying, I guess the reason I'm getting these wrong answers, guys, I'm putting in the wrong. Okay, this is... Okay, guys, that one's on me. It should have been, this is okay. The logic is fine, the specifics is not. The logic is fine, but this is not. You got to have this in here too. I'm sorry. Should have been evaluated to here. Everything else is fine. I mean, it's a careless mistake though. If I don't catch it, I get it wrong. It's as simple as that. All right. They said from t equals 1 to t equals 6. That's on me. All right, let's do it. Do the integral. Well, you did the integral. 2t squared integrated is 2/3 t cubed. 6t integrated, with respect to t. You integrate this with respect to t, you get 2/3 t cubed. Integrate this with respect to t, and you get 3t squared. You get all this. All right, let's put the 6 in here and figure out what we're doing here, guys. Delta theta, put a 6 in here. 6 squared, 36 times 3, 108. 6 cubed is 216 divided by 3 is 72 times 2, 144. 144 and 108 is 252. 144 plus 108 is 252. That's on this side. Put the 1 in here. 1 squared times 3, 3. 1 cubed times 2/3 is 2/3. That's 3 2/3. So when we do it, that's 250, that's 248 and 1/3. Now, they may not want you to write fractions. What are you going to do? 248 and 1/3 is 248.33. 248.333. You know, obviously it goes on forever, the 1/3, when you do a decimal expansion. But that's kind of where they're coming from, guys. You're going to look at it. And that's it. That's the end of it. Sorry about that, guys. I was gonna terminate this thing at 252. It would terminate at 252 if t was equal to 0, because if t was equal to 0, these do give 0. These yield 0 for t equals 0. For t equals 1, this yields 3 2/3. For t equals 6, yields 252. Do the subtraction, you get 248 and 1/3 radians. So you're integrating this sum. The integral of a sum is the sum of the integrals. Make a long story short, do what you know how to do, guys, and you're going to be fine. You can do this well. Okay. Watch what you're doing. It's easy. It's easy for this not to go the way you need it to go sometimes. So always be checking yourself what you're doing. There's nothing wrong with making a mistake as long as you can catch it. You got to catch yourself. You got to correct yourself. You're not going to say and do everything perfectly the first time you do anything. Or at least oftentimes it doesn't work that way. Okay, sometimes that happens, but not every single time you do something you're going to do it completely right. But if you can check yourself what's going on, very much of the time you can get things right, and that bodes well for you and much of what you're trying to do in your endeavors. Okay. All right, guys, I appreciate your time. We will talk more the next time we get together. That's some conversation about some of the problems related to Chapter 12 from Physics 209, the Katz book. Thank you much. We'll see you soon.